We continue on our interference and RM day today, and it's my great pleasure to have Massinissa here, who is come over from France, from Paris.
Yeah, despite the strike.
There was a strike as usual, so
Yeah.
that's quite the normal state of Air France, I presume. And so we're glad you made it, actually, for today. I'm surprised, actually, that they strike on Wednesdays, because Wednesday is a day where...
For all the week.
The whole week, all right.
Yeah.
Usually,
We don't do a day. I mean, it's
okay,
useless.
usually the strike is on Tuesdays and Thursdays, not too close to the weekend.
No, I mean, you just take all the week.
Okay,
Easier.
all right. I had scheduled you on purpose on Wednesday, thinking that Thursday and Tuesday you might have been on. Okay. Anyway, so we're here. He's got very strong background in physical layer, got his Ph.D. in 2006 in France, worked for Orange for a few years before he started working with Sagemcom. Together with Thierry Lestable, whom we had here on Monday. We're together in a project, Femto. So he's going to explain us essentially Sagemcom's his vision on how interference can be managed in femtocells. Close it all yours.
Yeah, thanks, Misha. Okay, and good morning, everyone. Massinissa Lalam from Sagemcom. Yeah, I think it's on. No?
Yeah.
It's on? No problem? Okay. So it's my pleasure to be here. I took a Spanish company so that I'm sure to be on time for this talk. So I'm going to talk about interference management in co-channel femtocell deployment. You may recognize many topics that we address, that my previous colleagues addressed, let's say this morning or even the day before, but repetition is always good. So the outline of my presentation will be to talk about the femtocell deployment, and in particular the worst case scenario, which is the co-channel in downlink when the macrocell user is in the vicinity of a femtocell. Basically, this is the, let's say, starting point when you're doing research on femtocell. Then I will just give an overview on the 3GPP status on interference management. As you know, there are plenty of topics that were mentioned this morning by Zubin. Basically, the ICIC framework and so on. And then I'm going to talk about how we can evaluate the performance of such interference management schemes that we develop or that are proposed by 3GPP using system-level simulation. I'm not sure that every one of you is aware on how we do system-level simulations. No? Yes? Everyone has already heard about that? I mean, if you're all an expert in that field, so you'll find this part quite easy and relaxing, so you'll be able to check your SMS and so on. But after this presentation, this part on system-level simulation, we'll talk about this famous dual stripe, green model, and so on that you've already heard. Then we just give some kind of result on some kind of performance evaluation on power control and some famous frequency partitioning schemes, all related to femtocells. Before concluding, and then we'll be able to launch. So, as it's already known, the femtocells are, let's say, more usually deployed by the users, meaning that operators do not have any control on their locations. But basically, this makes the network planning a bit hard. So, femtocell is seen as a small cell in the 3GPP terminology. In the 3GPP terminology, small cells, you've got femtocells and you've got picocells. Picocells that are the smallest cells that are, let's say, controlled by the operator when he's deploying them. Okay, but just to say that this is the frontier that we've got between picocells and femtocells. And femtocells, they are user deployed in some. Well, you can buy one, or it depends on the operator policy. And at the end of the day, you've got this cellular access at your home. And there is three policies that are coming with the femtocells when you want to access the cellular network. You've got the closed access policy, meaning that there is a list, a closed subscriber group list, and if you do not belong to this list, then you're not allowed to connect to the femtocell to have access to the network, to the cellular network. Then you've got some kind of open access, meaning that, okay, everyone is invited to the party, you can just come. It's open bar and so on. And you've got some kind of hybrid access, meaning that, okay, everyone is invited, but there is a VIP room. And this VIP room is just for the one who's paying the femtocell, or what you have to know is that a femtocell, to be able to connect to the network or to the core network of the operator, it goes through the DSL line or the broadband line of the subscriber. So meaning that the one who is paying will have, let's say, this VIP status. And as mentioned before, since spectrum is a scarce resource, co-channel deployment has received a lot of interest because, this spectrum is paid a bit amount of money by operators, so they want to reuse it at maximum. But with this co-channel deployment, meaning that we've got the same carrier for both the macrocell and the femtocell, there is some kind of worst case, especially with in the downlink with this closed access policy. It's true that when you've got your femtocells and you're here, okay, you've got a great connections, but if a macro user comes nearby and he does not belong to your CSG list, then he will suffer severe interference. The same for another femtocell users which do not belong to the same CSG as the one that you've got. So basically, if this is a neighbor that you don't like, it's okay. But for an operator point of view, this is a customer, so we have to take careful care on this kind of situations. So that's why we need some kind of interference management solutions. So for this talk, I will mainly put my focus on this downlink with a closed access policy. But this closed access policy will be either independent for each femtocell, or we can envisage that a group of femtocells will share the same CSG. Yes, please. Because when you're in, as mentioned by Zubin this morning, when you're in the downlink, this is when you can check, for instance, information that are broadcasted by the network. Okay, this is in downlink. If you're not allowed to access to the femtocell, you cannot basically what the femtocell is transmitting. Okay, you will be able to decode it, but since you do not belong to the CSG list of the femtocell, you will not be able to connect to the femtocells. Okay, and since this femtocell is transmitting, or you see that you receive a power which is higher coming from this femtocell than from the macrocell, you won't be able either to detect some things coming from the macrocell. Okay, basically this is why this is the worst case, because you don't have access anymore. You cannot receive. But this closed access policy, okay, this is just like your Wi-Fi router and so on. You don't want anyone to be able to connect. That's how life is working. So, this will be the main scenario, the main focus. There are other issues in the uplink, for instance, but okay, I want to address that today. So you have any questions? No? I think it's quite clear. So to start, I will just recall the 3GPP status on interference management, as Zubin talked about this morning. So you will find redundancy and so on, but I think that repetition is always good. And just before entering into this IC-IC intercell interference coordination mechanisms, you have to have the architecture in mind, the overall architecture. E node B is basically a macrocell or a picocell or a microcell. Those are basically deployed by the operator. Okay, they are connected to the MME mobility management entity and the serving gateway to then be able to connect to the core network of the operator, and this is done through the S1 interface. Okay, And some kind of new features introduced by LTE are this X2 interface that are connecting E node B to each other. I mean, those are just logical links, and you can, let's say, only for the time of the, let's say, release 9 and release, up to release 9, only macrocell, microcell, and picocell were allowed to have this X2 interface. Okay. Then we've got our home E node B. Basically, this is the 3GPP femtocell name. Okay. And those femtocells can connect directly to the network using this MME or serving gateway. Okay. Or they can go through some kind of gateway, the home E node B gateway with an S1 interface, and then this gateway connects to the MME and serving gateway. For a E node B, this gateway is seen as an MME, and for the MME, let's say this gateway is seen as an E node B. Okay, just to have an idea. And this use of gateway, I mean, this is to have some kind of concentrator. And if you think about the actual femtocell that are deployed, which are 3G or HSPA femtocells, they all use a home node B gateway. They all connect to the core network using this architecture. Okay. And what's new in the release 10 of the 3GPP is that you may have some kind of X2 connections between E node Bs, but between specific E node Bs. I mean, it really depends on the, let's say, CSG policy that you apply on the home E node B. So this.
How do we decide the scope of this connectivity? Means in a building, all of the home E node Bs need to be connected, or what?
What do you mean by connectivity?
Means the X2 interface.
The X2 interface. Well, usually these X2 interfaces are meant for femtocell that are, or base stations that are, let's say, that may interact with each other. I mean, X2 is used, of course, for interference, for IC mechanism, but it's also used for handover. To facilitate the handover, you use the X2 interface. Basically, those home node, those E node Bs, they have to be, let's say, some, not really in the vicinity, but they must, let's say, have a way to interconnect to each other. I mean,
okay. When
separate E node Bs. So to go back to your question about the femtocells, yes, those are basically X2 between femtocells which are, let's say, in the same building.
Same building. It's based on spatial co-location.
Yeah, it makes more sense. And you have to think about some X2 as well. Your X2 interface, it needs to be fast. Okay?
Okay.
Because through this interface, many data are going to transit and so on. And this has to be fast.
Okay. And for E node Bs, it seems to be star topology. Every E node B is connected to all of the other two E node Bs. But for each E node Bs,
I mean, in the specification, one E node B can set up an X2 connection to any E node Bs.
More than one. Means, okay.
Well, I mean, it's direct link, but I mean, everything is linked.
Yeah, but here for example, we have just linear connectivity. One for home E node B, one home E node B is connected to only one home E node B.
Yeah.
But there we seem to be connected with multiple E node. It is on purpose, or it's just for explaining?
I mean, just the scheme. I mean, usually, your E node B can set up X2 connection to different E node Bs. The same goes for the E node B. But those has to be, let's say, they must share the same CSG or have some kind of special status. Let's say they are open or hybrid. Because if you consider that you have a CSG there and a different one there, then this X2 interface has no meaning at all.
Okay.
Unless you're doing some kind of, let's say, interference mitigation stuff and so on. But I mean, this is not the priority right now to address this issue.
Okay. Thank you.
Any other questions? Okay, and then a final recall on the different access policy that you've got, the closed, the hybrid, and the open. But the thing is that you have to keep this architecture in mind. So X2 interface between eNode Bs, and the home eNode Bs may have X2 interface, but they rely on S1 more than X2 usually. So just an overview on the IC technique, intercell interference coordination. In release 8.9, so we're talking about LTE, not LTE advanced, so meaning just one carrier. The solutions that were proposed to do this IC, and that are standardized, are, let's say, frequency domain solutions. And they aim to provide a protection on the data channels. Okay? And this is done, so this is the release 8.9 architecture, and this is done through by exchanging some indicators through the X2 interface. So that means that only macrocell and picocell can use these mechanisms, these indicators, when they are release 8, release 9 compliant. Okay, and to let's say you've got the uplink interference management. So you've got two different indicators. This is how you've got the SCFDMA access for the LTE uplink. I won't go back to that unless there are some questions, but I think that you saw that yesterday. But basically the idea is that you've got the overload indicator. That means that one eNode B will report its level of interference on each resource block. I think that you're all aware with what a resource block is. This is a granularity. This is the lowest granularity that you can address on the OFDMA access. And one eNode B will report its level of interference. It's either low, medium, or high on each of these resource blocks. So this is a reactive process. It just sniffs this uplink bound, see if it receives too much interference on, let's say, a set of resource blocks, and send these indicators, low, high, medium, for all resource blocks to the neighboring eNode Bs. Let it be macrocell or picocell. Then you've got what is called the high interference indicator, where it's a bit different. This is not a reactive process, this is a proactive process. Basically, the base station will say, okay, I will send 1 bit per resource block, so it's a bitmap, and it will indicate that it indicates that cell edge users will be on these resource blocks. So basically, we're going to say, okay, this resource block, I'm going to put cell edge users. So this is some kind of user we have to protect. So I'm sending that, broadcasting that through X2 interface to other neighboring eNode Bs, and then they do whatever they want with that information. But at least I've warned them that they're going to be, I'm going really to have to have resource blocks that are really dedicated to cell edge users. Okay, and this
is a continuous process. Overload indicator is always transmitted.
When an X2 connection is set up, you can you can decide how many times you want to transmit that. The thing is that in 3GPP you're just specifying means, tools, okay. And then it's up to you to do what you want with that, with those tools, because it's all intellectual property stuff and so on. I mean, they just say, okay, in release 8.9 you've got that. Mm-hmm. Okay, do whatever you want with those.
Okay, this is just a requirement.
I mean, those are requirements. If you want to say, okay, I'm supporting X2 interface release 8, release 9, I need to have a way to set up an X2 connection to enable, and then to send up those indicators for the uplink, for instance.
But I'm trying to understand the purpose of this low indicator. Means why to send the indicator saying that there's low interference? It could be taken as default, and we could save some 1 bit.
Well, why did they make this kind of distinction? It could have been just low, high.
Yes, means medium or high. Means if there is low indicator, means there could be no need to transmit. Yeah.
I mean, those are just quantification. The more you bring, the more degrees of freedom you've got. Okay.
Okay.
I mean, this will also affect all your scheduling that you developed in the E-node-Bs. Yeah.
Yes, but with medium or high, we could have just one bit, yeah.
Yeah.
And means by sending low, we are not providing any information. Means it could be taken as a default scenario.
Well, but this is
yeah.
But this is some kind of, let's say, a reactive process. I mean, I'm sensing my surrounding, and then I say, okay, on those I'm okay. On those it depends. On those one, I'm really suffering. Okay. So this gives this level of freedom. I mean.
Okay.
But yeah. So this is for the uplink, and in release 8.9, you've got something else in the other way. In the downlink, you've got this RNTP indicator, relative narrowband transmit power, where in fact the E-node-Bs will just say per resource block what is going to be its transmit power. Okay, so this is as well some kind of proactive process, and it enables all this frequency partitioning scheme. Let's say one cell can advertise that okay, it's going to transmit a lot of power in this part of the spectrum, in this lower part. The second one in the medium part of the spectrum, and the third one in the high part of the spectrum. And then it enables some kind of dynamic frequency partitioning schemes. So you've got the hard frequency reuse, where you just split, you make orthogonality. Orthogonality is interference. I mean, it's a friend of interference. You lower the interference with orthogonality, but you lower your data rate and so on. You've got other schemes that are fractional frequency reuse schemes, where in fact you just make some kind of distinction. As Zubin mentioned, in LTE you want to protect the cell edge users. Or basically the ITUA requirements that have put some kind of stress on this cell edge minimum spectral efficiency that you have to provide to those kind of users. Because of course with LTE-A, with this 100 of megahertz and so on, you've got high peak data rates. But at the end of the day, you don't have that on your mobile phone. You're just one user among others, and you try to, let's say, put more stress on the cell edge users. So the idea of the fractional frequency reuse is to, I will go back on that earlier, but just to have the main idea is that, okay, you've got your central users that are close to the base station, so they've got good radio conditions. In three different cells, they may share the same spectrum, since due to geometrical factors, they won't be that much interfered. And then for the cell edge users, for the fractional frequency reuse, you give them orthogonal part of the spectrum, okay? And for, or you've got the other option, which is the soft frequency reuse, where in fact you're using all the bandwidth, but for these cell edge users, you're transmitting information or data to them with a higher transmit power. Okay, so basically, you're using all the spectrum there, you're doing some kind of orthogonality. But we'll go back to that later on. But all this, those are really for data channels. Because those data channels, we have got some kind of control on where to put, where to allocate resources to one user. While for the control channels, it's a bit more difficult. You don't have this flexibility. As mentioned this morning, these control channels are depending on your physical cell ID and so on. So you don't have this flexibility. The only flexibility that you've got, or you can play with, is, for instance, as mentioned, playing with the physical cell ID. But you have to keep in mind that you don't have that much of degrees of freedom, especially if you want to, you've got a limited set of physical cell ID, okay? And if you want to address the, let's say, reference signal interference, the cell reference signal interference, those ones are shifting with a modulo 6 for just one antenna port, meaning that when you have those nice macro base station with several antennas, let's say 2 antennas, it's just enough, or 4, then you don't have this modulo 6 flexibility, but it's a modulus 3. So this limits a bit all that. But fortunately, cell reference signals are known signals, so we can put a stress on the UE to use advanced receivers. But I mean, this is what's being discussed now. But okay, so far release 8 and 9 for ICIC, it was really for data channel protections, and those were frequency domain solutions. Okay. Then with release 10, we've got what we call the enhanced ICIC. So you'll see this EICIC quite often if you're familiar with heterogeneous networks, the EThnets. And basically, this EICIC targets those kind of deployment, those EThnets. Main of these ICIC means that are provided, those are time domain solutions, and it's meant to protect the control channel this time. So we've got still some information that are exchanged through X2 interface. So we've got this E0B, E0B X2 interface. We've got as well X2 interface. So when we're going to exchange information through X2 interface, basically we're just saying that, okay, this will be some kind of macro pico scenarios, okay? No femto, because femto cannot have X2 connections toward a macro or a pico or a macro, okay? So this is X2 interface. And to encompass femtocells into those HETnet scenarios, then we can rely on, let's say, static or semi-static configurations. What you've got to know, and I think that they will, I don't know if you've seen already the architecture so far or not, but home E0B, it has what's called an HMS, which is an auto configuration server, and it provides to the femtocell some information on, let's say, the carrier you're allowed to transmit on, your maximum power, and so on. And you can as well exchange information using the TR069 protocol, which is a protocol coming from the Broadband Forum, really targeted to CPE, customer premise equipment. And you will use this protocol to have, let's say, to define some kind of semi-static configurations, and to provide information to the femtocell. And despite being a release 10 mechanism, the focus is only on non-carrier aggregation deployment. I mean, just have one carrier. This is the idea. So what we've got the downlink power control. Basically, this targets the femtocell, where the power of the femtocell is adjusted based on its surrounding. And measurements are performed in the downlink and in the uplink. And to do that, you need to have, let's say, a network listen module within the femtocell, which is, let's say, a piece of hardware which is doing the same measurements as a UE would do. Okay? You have to know that in the specifications, the femtocell is still a base station. So it has some kind of measurements that it has to do, it has to perform, but not all measurements. I mean, the base station could only measure, let's say, the specific power coming from another base station, but it cannot go that far. It cannot do the same measurements as a UE. It's not specified. But operators, when they order you a femtocell, they say, okay, I want that. I want that features. So you have to implement that. And okay, the ID, it's not expressly, I mean, this is not this expression that you may find in the specifications, but it's the same. You will have, that you will find it's something that, okay, my new, I'm doing some kind of sniffing. Okay, my femtocell is doing sniffing. It measures a power coming from, let's say, the dominant macrocell base station. Okay, and then I'm just correcting it with some kind of parameters, okay, which will, let's say, for instance, this parameter will define my coverage radius, okay? And I'm doing that in the range of the transmit power that a femtocell can support. So I'm sniffing the macrocell environment, and I'm adapting just my power to protect, basically, the macrocell user that may come in the vicinity of this femtocell. The idea is to keep the coverage area of the femtocell, let's say, close to the femto users, but not going too far away. If you go back to the specification of femtocell, you know, you can see that let's say a femtocell can transmit at maximum power. I think it's 23 dBm or 23 dBm when you've got just one antenna, and 20 dBm per antenna if you've got two transmit antennas. But when you transmit with that much power, I mean, you're just disturbing too much the macrocell network, especially if you're in a residential scenario. I mean, just to, okay, I want the femto just for myself, covering my house or my apartment. So usually you need less much power than that. It's around 0 dBm, but okay. Those are just average number. So downlink power control has been introduced, and we see some kind of evaluation after that. What's new as well is what Zubin mentioned, the almost blank subframe pattern. I mean, the idea is just, okay, on certain subframe, I will just mute. Okay? I will just mute. So that the aggressor cell will just mute its transmission, and the victim cells will be able to, let's say, transmit normally, and the users may be able to, well, have access to the network and so on. But as mentioned, there are some issues with the mobile that needs to be aware of these patterns and so on, and those are current discussions. But at least patterns were defined. You have a question? No? Oh, okay, sorry. But you've got patterns that are defined and patterns that have some kind of, let's say, periodicity, because you know that periodically on the downlink, some broadcast channels are transmitted, and you want to protect those ones, the PSS, the SSS, and so on. And the thing is that those patterns, they are dynamically transferred through the X2 interface. So we are just talking about the macro pico scenario. And in such case, I mean, the aggressor is the macrocell and the victim is the picocell. While on the opposite way, when you're trying to apply almost blank subframe to femtocells, then it's the other way around. I mean, the aggressor is the femtocell and the victim is the macrocell. And those patterns are semi-statically broadcasted. I mean, they're using the what we call OAM, Operations, Administration, and Management. This is the configuration server that we saw just in Release 10 architecture, this HMS stuff. So with almost blocks, with ABS frame, of course, you just transmit those cell reference signals that may be some kind of that may give interference, but those signals, I mean, they are known. They are part of a special sequences. I think it's Shuzadov, but I'm not sure about that right now. But can check. But anyway. Those are known sequences, meaning that we can put intelligence on the receiver side. But putting intelligence on the receiver side, I mean, it's always not that. It consumes battery, okay? And you may, let's say, use interference cancellation mechanism. You know what you know what is the real structure of these CRS. You can suppress them at the receiver. but you cannot specify in 3GPP, I'm going to use interference cancellation. No, you're only going to specify requirements. With this level of SINR, I can decode. So this is a bit, I mean, this is the game. At the end of the day, on the 3GPP side, you cannot specify receive techniques or more specific receive techniques. And what you've got as well is what's called the cell range extension. I mean, this kind of thing targets especially the hotspot scenario on the meaning the picocell deployment, where in fact the picocell is going to broadcast a bias, and when a UE is close to the picocell, it reads the system information, which is broadcasted by these picocells, and it's doing its measurements to know, okay, if I was in idle mode, I was comping on this macrocell, should I go and comp on this picocell instead, because it offers a better, let's say, receive power. But this mechanism, to do that, there is an offset, which is broadcasted. And if you just modify this offset, in fact, you can tell to the UE, okay, stick to the, or comp to the picocell, but in fact, its SINR level will be low, okay? Because you introduce some kind of bias, and it say, okay, I will stick because this is broadcasted this way, but I'm experiencing a lot of interference, and this is where, to cope with that, you need advanced UO receiver. Okay, let's, for instance, interference cancellation receiver and so on. Yep.
What's the notice then, if I would like to
The idea of this cell range extension is in a hotspot situation. You want to get you want that the people that are connecting to this hotspot stay on this picocell and do not, let's say, overload or do whatever you want on the macro network. They have to stay on the pico to offload the macro network, which covers a greater area.
Bias towards the...
So it's a bias toward, I mean, it's the bias broadcasted by the picocell, and it's, for instance, you need X dB, you need to have, let's say, X dBm to comp on this picocell, and then you will just add a bias, and you will say, okay, you need X minus that, you need less power to comp on this picocell. This is meant to stuck people or to stick people into this area. Okay, so this is some kind of a flow, but you need advanced receivers. And all that are for, let's, non-carrier aggregation system. Any questions so far? No? So in release 11, I mean, the current discussion that are occurring in 3GPP, you've got, let's say, two different approaches. You've got the further enhanced IC for non-CA-based deployment, meaning that you're just enhancing a bit further what's existing, but just for the non-CA-based deployment. So there are proposals that are that you can. I mean, I don't know if you're following the 3GPP discussions. If not, you can. I encourage you to follow those run 1, run 4 as well. Reflector. Just, I mean, I think it's almost free, and it's a source of information. But it's a source of disturbing for your mailbox, because every month you've got hundreds of megas that are on your box. But apart from that, you will see these kind of discussions occurring on those various topics, and you've got this FE, IC stuff, where there is some kind of things at the, there are some proposals at the transmitter side, let's say, where we say, okay, we will combine the almost blank subframe pattern that we've got, but we will add power control on top of that, just to reduce the complexity or the need to decode the cell reference signal from the blanking subframe that are still there. And of course, you've got as well this advanced UE stuff, advanced UE receiver stuff that are discussed and bring back to the table, cancellation, discard of non-signal, and so on. And what's new is that you've got, okay, the IC, but this time for carrier aggregation-based scenario. So I won't go back to the carrier aggregation, but okay, I think Zubin made it clear how it's working. At maximum, you've got 5 component carriers. And for these component carriers, you've got one per user, which is defined, which is the primary component carriers, which will, let's say, have this, the control information telling you where your data are located in the other component carriers. And those other component carriers are called second component carriers, second cells. And you will find, and what it's worth noting is that cross-scheduling is possible, meaning that you can have on one component carrier controls that tells you, okay, you will have your data on the same component carriers, but as well on the second one component carriers and so on. So the idea is that, okay, that is just what I just told, is that the primary cell is carrying the control and or data information, while second cell are carrying the data. And the idea is to check or to see how we can distribute this component, these primary cells, these secondary cells, when we've got a carrier aggregation system. Because what you've got to remember is that those cells, primary and secondary, those concepts, they are per user. Okay, this is not for one base station, I've got one primary cell. No, this is for these users. This is my primary cell. So the idea is what has been discussed now. Okay, if I've got a macro user which is close to the base station, to the macro base station, okay, I can have my control on the component carrier 1 or 2, okay, and my data on 1 or 2, doesn't matter. But when I'm close to, let's say, a picocell, then I will just have for this macro user which is close to the picocell my control on a given component carriers and my data on F1 or F2. And for the pico users, I will have the opposite, to just protect the control channels, just as we saw this morning. I mean, the idea is really to protect the control channels, because without the control, you don't have the data. Then, if you have protected the control, then, okay, you can have a look at the data, how you can protect them again. But this is the idea. Any questions? No? Okay. So all of those are, let's say, the mechanisms that are discussed or that have been discussed in 3GPP those years. And no? Yep. Sorry.
The cell selection procedure takes into account only the SINR, or does it take into account the load as well? Load means the traffic load. For example, the picocell might provide, say, better SINR for somehow, but it may be loaded. So is 3GPP?
Yeah, okay. I mean, those are under discussion. Those are just proposal. Okay, the idea will be to do that. Mm-hmm. Okay, but of course you've got more than that. You've got the cell load. You've got all this kind of stuff that you may put on top of this mechanism. This mechanism just tell you, okay, your control will be, let's say, orthogonal, so you won't have any problem with that. Mm-hmm. But then if you decide to accept new users and so on, I mean, it's up to you to maybe as well use the cell range extension and so on, play with that. Or you can just deny an access to one UE. But when the UE is idle, you cannot deny any access. Okay? Okay. The femtocell can, or the base station. I mean, what you have to know is that a UE, when he's in idle mode, and he decided to camp on the base station, it does not tell the base station, okay, I'm here. It only tells that if I don't know, you've got your macrocell network, which is divided in small tracking area, okay? And when you're changing tracking areas, here the mobile has to advertise, not the base station, but the core network. Okay, I've changed my tracking area, I'm here. Why? Because if you want to receive a call, the core network needs to know where you are. Not necessarily which base station is serving you, because in idle you do not advertise that, but where you are, in which tracking area, and then it will send information to those base stations covering this tracking area to do the paging.
But in active mode, when a base station is...
When you're in connected mode, then of course you're there, you're just doing your measurements, and you just say, okay, oh, this base station is better suited to my SINR quality and so on. And then this is always your serving base station, which will trigger the handover, never the UE. The base stations will contact the target base stations, and will tell him, okay, handover is needed. And then these target base stations, if it's overloaded, it can say, okay, no, you won't be able, no, I cannot accept you.
Okay.
All those are, the handover is always, let's say, controlled by the base stations, never by the UE. It's only when you, in active mode, I mean connected mode, but in idle mode, the UE just can and never tell the base stations, at least when it stays in the same tracking area. No more questions? Okay. So we've got many of mechanisms to deal with interference, and how can we evaluate them? Of course, we could rely on link level simulations, but in the base case, because in link level simulations, you're really simulating everything. Your bit generations, your encoding. In the case of LTE, it's turbo encoding with code block segmentation and so on. Then you've got the modulations, the mapping, and the OFDM stuff, the channel, and this makes the link level simulations adapt to, let's say, a point-to-point, or in the base case, point-to-multi-point situation scenario, let's say some kind of multi-user scenario, but really one base station and some users. Not a large-scale evaluations. And that's where system level enters the arena, to provide you a large-scale vision of your algorithms, how they operate. So I'm going just to give the, let's say, classical evaluation methodology. Do you have any idea on system level simulations? Have some of you already done some? No? Yes? Just write the end and I know. Okay, so I think it will be worth for the others. So what you have to know is that these system level simulations, they allow large-scale representations, meaning several base stations, and attached to them several users. Okay, and it aims at evaluating all your system performance, meaning that you can evaluate radio resource management algorithms, interference mitigation techniques, coverage estimation, and so on. And based on those evaluations, you can gather statistics, because basically system level simulations are based on Monte Carlo approach. You can derive some kind of mathematical framework and so on to avoid those Monte Carlo approach, but at the end of the day, in 3GPP, for instance, Monte Carlo approach, this is where you've got your results. So you then, based from that, you can gather many statistics. Let's say, for instance, the throughput, the fairness, how many times a UE has received data. All this is based on your scheduling policy that you have implemented. So you can check your scheduling policy. You know that you've got 3 families of scheduling algorithms: the max C over I, the round robin, where you just schedule users independent of their radio channel quality. and you've got some kind of proportional fairness stuff that tries to, let's say, be a trade-off between the amount of data you received and your quality. You can measure as well cell activity. This is of interest for femtocells, for instance. And of course, you can apply realistic traffic on top of that. For instance, you can then estimate your frame packet error, all statistics that are related to traffic. For instance, the jitter or the frame packet acknowledgement time, and so on. And basically, the structure that you may, the evaluation methodology, either you're looking at 3GPP, 3GPP2, IEEE 802.16m, well, or WiMAX. You have always this kind of same methodology. You've got the system part, where you've got what is called a static construction, where you will build your network, you will deploy your mobile, and then you will compute your long-term parameters. Your long-term parameters encompass the path loss, okay, basically, the antenna gains, because you've got some antennas, especially for the macro cell network, which have a privileged direction, a bore site, and shadowing, of course. And this is the static. Then you enter the dynamic part, where you've got, let's say, some kind of loop. A loop based on the subframe granularity, on TTI granularity, where you compute all your short-term stuff, meaning basically the fast fading. Okay, here you just have your fast fading. Okay, based on that, you will have this what is called the physical layer abstraction, because as I told you, you cannot with this network deployment. I mean, the idea of to have many base stations, many users, do the link simulations. So you just use an abstraction. And usually, and I'll talk to that later, you can use lookup tables, which gives you, for instance, once you've computed one values, the SINR, the block error rate of your radio frame. Or you can use a more direct approach, which is, for instance, the truncated Shannon bound, which will use, from the SINR, gives you the spectral efficiency. It's quite straightforward. And then you've got this loop. Okay, you've got all that. You can report here the CQI and so on, and then you're doing your scheduling, and you can as well simulate the HARQ process and so on. And this loop, and during sufficient times, you can gather statistics, let's say throughput, coverage, and so on, for a given scenario, a given deployment. Then you can redraw or redrop all the network stuff and do the same again. And this is the Monte Carlo approach, and at the end, you gather statistics that you represent most of the time using a CDF. Those are the curves you saw this morning, for instance. So regarding the network deployment, for the macro cell, there is a 2D hexagonal layout where we talk about a central cell, okay? Usually you've got a base station at this location, which covers 3 sectors, okay? So basically you've got 3 cells. Okay, but they are located. The same base station is covering the 3 cells. You've got a first tier, which are 6 seats surrounding your central one, and with that you have now 7 seats, 21 cells. Okay, and you have to keep that value in mind, because for femtocell simulations we usually use this layout instead of the traditional one, which is you add a second tier with 12 seats, and this leads to a total of 57 cells. Okay, so this is the, let's see, hexagonal layout, this traditional layout that you've got. In each point, you've got a seat. Each seat is taking care of of 3 sectors, and each sector is a cell. Okay, so it's seen as a different stuff. So in terms of interference, it's sure that when you're here, you see a lot of interference coming from those from the first tier, from the second tier, and so on. But when you're, let's say, on the second tier, then if you just compute the interference just this way, you will have less interference, because due to the geometrical stuff, if you're there and you see who is going really to interfere you just have those cells. So the idea is to combat this edge effect by using wraparound. Wraparound is just, okay, I've got my cluster, my first cluster, and I will duplicate this one all around. Okay? So this allows to this allows that every user there will see an equivalent amount of interference. This is the idea. And wraparound is done only using a mathematical trick when you're computing the distance. And this avoids you to just have, let's say, because what was done previously, for instance, is that you can, okay, drop stick with that and gather results only for the central cell, for instance. But when you're dealing with, let's say, femtocell stuff and so on, they are deployed a bit everywhere. You do not guarantee that you will have cells at the exact positions or this kind of stuff. So relying on wraparound, okay, it's a bit more complicated, but you've got the overall picture. And it's complicated only with, it's just a mathematical trick to when you are computing your distance and so on. You can find everything on the, I think, Femtoforum white paper has got it right. The OVM-A1, you take a look at the annex and you have these equations on how to use wraparound. And then when you've got this network, then you can compute the long-term parameters. So if we consider that we've got a point P, okay, which is at a distance r from a seat or a base station, and which is doing an angle theta with the main direction of your cell, then you can, let's say, with this the geometrical stuff, you can derive the long-term parameters. You can derive the path loss. For instance, at 2 gigahertz, the path loss is given this way. So this is in dB, and you can add optional wall attenuations. So it makes sense when you are going to talk about femtocells to have these wall attenuations. You can derive the antenna gain. Usually your point, if it's a mobile, you assume that you've got an omni antenna pattern, because when you've got your phone, you do not really target your base station to know, okay, I've got a better reception this way or this way around. And this is some kind of usual pattern, 2D pattern that you've got for the base station, for the macro cell base station. Okay. For a femtocell, we as well assume that we've got omni, because your femtocell, you do not have any control on how it's going to be placed by your users, by the user that is going to buy your femtocell. So it's an omni diagram as well. Of course, you may have some refinement with the tilt, and then you're entering the 3D pattern, but it's an equation which is similar to this one. And of course, you've got this shadowing, because up to now, there were no random stuff at all. Once you've put all your base stations, all your users, it was fixed, the antenna gain, the path loss. And the shadowing, it's some kind of random variable. It's a log normal one, which represents, let's say, the obstacle that you may have between your base stations and your mobile, and your point. And there are some correlations, especially true for the macro cell, meaning that, okay, you've got a correlation of 1 if you are considering sectors or cells from the same site, because basically when you've got 2 points, independent of the sector that you are considering, the obstacle between those two will be the same. Okay? And a correlation of 0.5 between sectors or cells from different sets. So this is the basic assumptions. And with that, you can compute
Does this correlation coefficients come from any specifications? Otherwise,
you take a look at the any evaluation methodology. being it from 3GPP, from WiMAX, from IEEE 1102, 802,
Because
16M. You
there's
have
some
this kind of correlation. I mean, those are basic assumptions. This is the, let's say, those are your
assumptions, okay.
Those are how you compute shadowing. And there's optional stuff is when you just talk about autocorrelations. Because with this kind of approach, I've got one base station. I'm here. I'm experiencing a given shadowing. And if I've got, let's say, a friend just near me, he won't have this. Usually, its shadowing will be independent. This is the simplest way to compute shadowing. But, I mean, if you just think about, I mean, we experience some kind of equivalent shadowing. And this is, for instance, captured in the evaluation methodology document from IEEE 802.16m, where they introduce 2 degrees, where the spacing between your point defines the autocorrelation. So what we assume is that for a urban environment, you are around 50 meters, 50 meters for macrocell and 3 meters for femtocell.
Yeah, but my question is, this is cross correlation and that is autocorrelation.
Yeah, but for cross correlation, people are using that.
But there are some models in literature which give you based on angular spacing between base station and distance, relative distance between base stations.
What is true is that once you, when you're taking a look at how the fast fading coefficients are generated, take for example the special channel, the SCM channel, which is the MIMO channel. In fact, when you generating your shadowing, you're generating as well your angle spread and delay spread. And all of them are correlated, so you are adding more complexity to your shadowing generation. But you've got a better picture on how your how this affects your fast fading coefficients. And okay, but this is just practical on static case. This is what we usually do.
It's for simplicity. Otherwise, there is a more sophisticated model.
When you're going with fast fading, you still have those coefficients, but on top of that, your angle spread and delay spread and so on, they are correlated to the coefficients you generated.
Okay, thank you.
Just how you have the SCM.
Because this will make life very easy. Actually, it means we spend a lot of time in modeling shadowing, and these assumptions could save us.
This is just to have, let's say, a common basis, so that when you come with an interference algorithm, or when you're doing some kind of performance evaluation, let's say a MIMO scheme and so on, you can compare with other people and have a simple model to. So that you can, you're not forced to put a lot of efforts to have a common basis and then do this comparison.
Okay, thank you.
So with all those parameters, at a given point, we can compute the receive power coming from a base station, which will be its transmit power plus the gain, the antenna gains that we've got, that may encompass as well body loss. Usually they are put with the antenna gain and so on. And you just take out the path loss and the shadowing. So once you have defined your serving cell, you are able to compute the SINR, or called as well the G factor, the geometrical factor, because it relies on geometry, where you've got your receive the power from your serving base stations, and you just sum up all the interferers plus the thermal noise, which depends on your bandwidth and so on. But basically, this G factor, called a SINR or whatever you want, this is the static that you just check. And that, when you want to plot it, can give you some kind of nice picture that maybe you are friend with. This is when you do not have any shadowing and without wraparound. So here you see the edge effect that I was mentioning. Okay. And without shadowing, okay, I mean, you can, you don't have any randomness on that. everything is fixed because the antenna gains and the path loss are fixed once if you do not put any shadowing. And here, this is the same pictures when you just incorporate the shadowing, okay, plus the wraparound. So you don't have any edge effect anymore. But if you take a look, you maybe close it, maybe I don't know if you can see it here, but you see here some kind of grid because you will see this 50 meters autocorrelation stuff because here we implemented what I mentioned earlier. So this gives you, okay, you can evaluate a G factor anywhere. So what you're going to do is not evaluate it anywhere because of the shadowing. You want to just drop some kind of users, a given number of users, compute the G factor for those users, and drop again. This is the Monte Carlo approach. And this is what you're going to do for the macro cell. This is the basic stuff. Okay, then you've got this. You may have this kind of figures when you just put colors to where the user are attached to each cell. Any questions so far for the system level evaluation? No? And then on top of that comes the Femtocell. And what we've got there is that we've got two U-band models that are defined, and that Zubin mentioned this morning. You've got the famous dual stripe, where in fact you've got two stripes of 20 blocks. Okay, those are there. And you have to see that in, let's say, 3D, because you've got 6 floors, up to 6 floors. This is specified in the TR 36.8.14. And the path loss is given with these equations, where, in fact, okay, you've got a common path loss. If you're in the same stripe, okay, if your base station is there and your mobile is there, you're just using this part of the this path loss. And this one, if you're familiar with, but I'm not sure, this is the free space loss at 2 gigahertz. Okay, this is the free space loss. And to put a bit more attenuation or realistic propagation on top of that, you will just count the number of internal walls that are separating your base station from your point. So this is the P. P represents the number of internal walls that you will have to cross, and Q represents the number of external walls that you will have to cross. So usually for external walls, there is something like 10 or 20 dB of attenuations, and for internal walls, it's around 5 or 10 dB. It really depends. And you've got this this term, which is function of the distance, but just the indoor distance, and which represents, because here this is an apartment, but usually you don't have an apartment without internal walls. I mean, you have your rooms and so on, unless you, I don't know, don't like walls or so on. And this is some kind of, this factor represents the kind of small walls that you have to cross, or the rooms that you have to cross. Okay? Well, I don't remember exactly, but it's assuming something like a wall every 3 meters or something like that. But okay, it's not really worth remembering. And of course, we are assuming a shadowing, but of 4 dB of standard deviation. While in the macro cell case, it's usually 8 dB when you don't have this line of sight stuff. And if you are under 1 meter from your femtocell, there is no shadowing, basically, unless you put a door just there. The thing is that, yeah, and there is a last term that I forgot to mention, which is the last one, where M, in fact, is the difference in terms of flow that you've got with your femtocells and your users that you are considering. So this makes the dual stripe model a bit complicated to implement, quite frankly, because you have to, if you want to do it properly, you have to count every walls that you are going to cross, check if it's an internal or an external wall, check again the elevation where your user is and so on, but okay, this is the dual stripe model. So since it's a bit complicated, people have just said, okay, let's go for another model, the grid one. The grid is much more easier. You just have one floor. You've got 25 blocks, okay? And okay, those blocks are just here for you to see, okay, those are blocks. But at the end of the day, this is how I'm going to compute my path loss. Okay, I just have the distance, and that's it. I won't consider the walls at all. Okay, but to let's say the idea will be, okay, if I do not have wall, I will just increase my shadowing standard deviation. So I have got 10 dB of standard deviation instead of 4. But this makes the grid model, when you're applying it with this path loss, this makes it a more aggressive femto to femto scenario. And it's not as compartmented, as split as the dual stripe. But the dual stripe, as I've told you, I mean, this is free space loss, this is a number of folds that you cross, so you could perfectly apply the previous equations to this model. I mean, it will work the same way. But the grid was used in run 4, I think, because in run 4, they're just more focused on performance evaluations, and they do not want to have that complicated schemes for the femtocells. So at the end of the day, you choose either one or the second clusters or models, and you just have a deployment probability, meaning that in each block you have X % chance of having a femtocell or not. And if you have one femtocell, then you will drop users within the same block, with considering a minimum femto user distance of 20 centimeters. For the macro cell, you've got something like 35 meters of minimum distance, so that your path loss equations are still correct. But I mean, this just gives you a scale. I mean, we just taking apartment with 10 meters cost 10 meters. I mean, those are quite nice apartments. And all those were static. I mean, this is just static. Okay. When you enter into the dynamic world of the system level simulations, this is where you've got the fast fading. This is where you've got all those subcarriers. This is where you compute using realistic receiver, let's say MMSE receiver or maximum ratio combining receiver, which gives you for one user, for instance, an SINR on each of the subcarriers. So we've got if we consider an LTE system with 10 megahertz, we've got 600 subcarriers. Okay, so we cannot have these 600 subcarriers, these 600 SINRs, and deal with that. No, we use compression. And compression, the idea is to, okay, compress. So you've got this 600, and you just go to one value that is that has a meaning, that do not deteriorate your performance when you're doing link level simulations. And in terms of compressions, you've got, let's say, the traditional EESM. It is an exponential. You're using an exponential function to compress that. The thing is that this compression, it relies on parameters that are dependent on the modulation and coding scheme that you are using. So you have to tune those parameters when you're using the EESM to each modulation and coding scheme that you're going to exploit, okay, or to use. And you've got the MI-ESM, which rely on the mutual information. And when you're using the mutual information as a compression function, and you try to tune those parameters, then you see that, in fact, you do not need these parameters because their value are quite close to 1. So people tend to use the mutual information for compression. I mean, saves the day. Or you can use more hard approach, such as the WiMAX, for instance, methodology. I think they're using the capacity. You're using the capacity. But anyway, you're just talking about exponential and then logarithm to do the compression.
But
the thing is that in your compression, you're just applying a function to the, let's say, I should have put the equations, but I thought too much equation is a bit hard to digest. But at the end of the day, maybe I can. You've got your compression function, okay, that you're going to apply to, let's say, your SINR. You're going to put a parameters. You're going to sum that on all your subcarriers, for instance, and then use the inverse function and put a parameter. I think well, it really depends. Some people tend to use the same parameters. Okay. The thing is that this will be true, and you have to check beta or an alpha or a combination of both. When you're doing EESM, you have to tune those to the modulation and encoding scheme that you are using. Okay. Why when you're doing the same, but using instead of using this exponential function, but you use the mutual information, then you do the same, and you see that your beta and your alpha, they are close to 1. So you don't really need to rely on that. So this is the, let's say, advantage of the mutual information compression. But all that is just to go to just one value, the SINR, that you have computed using, let's say, since you've got fast fading, you use receivers where you can easily compute the SINR, MMSE, MRC. Well, that's it. Because for the MLD, if you've got something, I'll take it. And what do you do when you've got this final SINR, which represents the overall quality that your user is experiencing, that you have computed either on all, either on all the all the subcarriers or just the part that you are interested in. You can rely on lookup tables, which give you the block error rate, this is the SINR for all the MCS, okay? Or you can use what has been mentioned this morning, the truncated Shannon bound, which gives you directly the spectral efficiency. You just have this, this Shannon bound, okay? And you just say, okay, I've got a maximum spectral efficiency that I cannot exceed due to, let's say, modulation order. And from that, okay, you will have your spectral efficiency and you can compute everything. So this is the idea of the system-level simulations and what you can do with that. And what we can do with that is, for instance, evaluate the power control scheme that we saw previously. Okay. So the system will be based on 10 megahertz bandwidth, 2 gigahertz over the carrier frequency. This is a Euroband deployment scenario where the interseed distance is 500 meters. For femtocells, we tend to use 7 seats instead of 19 to reduce the simulation complexity. And what we decide is to do some kind of static evaluation. So we are dropping a lot of users in the macro, and we are ensuring that 35% of them will be in the cluster that will have femtocell within. Okay, those are just a recall of the parameters that we've got. And we will just, for these simulations, just consider the 5x5 grids, which mean the aggressive femto to femto models, and assume a 15% deployment probability. And this minimum maximum power will be 10 dBm minus 10 dBm. And when we are computing the CDF, the CDF of the G factor and assuming an independent CSG per femtocell, meaning that when we've got two femtocells close to each other, they cannot, let's say, they do not share the same CSG. And I used to have some dashed curves, but okay, those one are the dashed curves. In red, you've got the macro cell. In blue, you've got the femtocells. And what we saw is that basically applying power control tends to, of course, lower the femtocell user performance because they've got less power. But in the same time, it increased the macro cell user performance. So if we just take a look at what we call the outage is when your G factor or the SINR is below a given value, which tells you that, okay, it won't be possible to connect or to have access to the network. And you just consider that this value is, for instance, minus 6 dB. Then when you're doing nothing and you're just ensuring that 35% of your macrocell users are within the grid, you've got 20% of your users that are in outage. Okay? And for the femto users, you've got 10% of them which are also in outage because you've got independent CSG, and you have chosen this 5x5 grid, which is the most aggressive femto to femto scenario. Of course, when you're applying power control, these values goes down. And if you take a look at your average transmit power, instead of your 10 dBm that you've got, which are fixed for all femtocells, then you're more around, let's say, minus 1 dBm. And to have something like, okay, I'm below 10% of outage for my macrocell user, but it's still high. I mean, it's still high. This is just to give you a picture. And what you can do as well is, okay, since you're in the same building, you have, I mean, you've got the same, let's say, same carrier. So basically, you've got the same operator. You can say, okay, all my femtocells will have a common CSG. Just by doing that, of course, you will greatly reduce the femtocell outage because the femtocell user was previously disturbed by other femtocells. Now we can connect to them. So basically, you have no more outage. And still have equivalent values for the macrocell user outage. And with the same power control, which will lead you to the same values of average power, then you reduce a bit more the macrocell user outage. But the increase in femtocell, since you have reduced the power, you still increase the femtocell user outage. But it's still below 1%. I mean, it's even below 0.1%, so it's negligible. And, well, maybe I can skip this. I think we will have the slide. I'm not sure about that. But, yeah. So this is just the same scenario, but using the dual stripe, which is more femto to femto friendly. And you see that with the outage, which is really low, because you have got all these walls that are protecting all your femtos, even with independent CSG, while, of course, when you go with common CSG, it's far below what we've got previously. And in terms of outage, due to the protection that you've got, because you've got this really low wall modeling and so on, you've got some kind of more realistic model. It's not perfect. I mean, there are plenty of room to improve it, but you still have this wall modeling which protects you and so on. And then you go back to outages that are below 3%. And those are the things that you can do with static simulation to evaluate this femtocell power control. I mean, this is just the basic of power control when you just have this low deployment probability. Of course, when you increase the deployment probability, then you have more femto to femto interactions, and then you have to take those interactions into consideration when designing your power control algorithm. Those are just, I mean, the classic one. Just take care of the macrocell. So you can, there is room to improve that. And we've done that in the femto. And of course, you can go to, let's say, evaluation of frequency partitioning schemes and evaluate them in a dynamic way this time. So the classical schemes are the fractional frequency reuse. I'm not sure I'm going to talk about that again, but you're doing for your select users some kind of orthogonal frequencies. You allocate them and you compare that with the soft frequency reuse where you boost their power. But what you've got to know is that, okay, these are the principles. But in LTE, you do not split or address the spectrum the way you want. In LTE, you've got what we call the resource block that you are familiar with. Those are the 12 subcarriers that you are gathering together. Either either they are continuous, or they may be discontinuous, but most of the time it's continuous. And for instance, for the 10 megahertz bandwidth, you've got 15 resource blocks that are paired. Resource block group, and usually one resource block group, what is it? It's 3 resource blocks. And these resource block group are either grouped again in subband. A subband usually is a set of 2 resource block groups. And these subband are gathered together into bandwidth parts. Okay? All that has a meaning, because when you have this spectrum, what's happening is that, okay, when you want to tell a UE you will have data on this resource blocks, you cannot have this bitmap of 50 resource blocks. I mean, it's a lot of signaling that you have. So you have to gather and just put together some stuff. And for instance, the allocation type 0, which is used in specification, it allows you to have this to give to users any resource block groups of this set. I mean, any one. So it's a bitmap. And for 10 megahertz, it's a 70 bitmap. Okay? And you see that you've got some kind of last subband, last resource block group, which do not have the same, exactly the same size of the others. But you have to keep that in mind, because, okay, this is how you tell a UE you will have information on that resource block groups. And the thing is that your UE is just reporting you, in the best case, at this granularity, the subband one, when you're talking about periodic reporting. It just gives you, okay, this is my quality over the whole bandwidth, or this is my quality, let's say it will report you by shifting for each bandwidth part, which is its best subband. So, and you can, let's say, do aperiodic reporting and say, okay, I want all the subbands, and so on. And just to tell, to have that in mind, okay, you will have for the specific LTE partitioning what we have what we have chosen for the results that we've got just below. And of course, since the last subband is the smallest one, we've tried to have the dedicated cell edge bands at the beginning of the spectrum. And if we are comparing fractional frequency reuse, soft frequency reuse, and of course the reuse 1 strategy, which is the IFR in this, well, you see that let's say the fractional frequency reuse, due to orthogonality, well, will give the highest SINR for the users. So in terms of CDF, this is the one which will be the blue one. So for a macro cell layout, you can rely on FFR, and on top of that, and I will just put that, you can put femtocell on top of that, and put on top of this kind of FFR scheme for the macro cell, and just say, okay, for your femtocell, you will only use 2 subbands for the time being. This is just a scenario. You can use the whole bandwidth, but you can just choose 2 subbands that you have, that you will choose by sniffing, for instance. And those are, again, the dash should have appeared, but anyway, you can evaluate what you've got in terms of cell throughput for the CISO case, for the 2x2 MIMO case, and for the 4x4 MIMO case as well. For the macro cell, and since you have limited your subband to the femtocells, you are reaching a maximum values. And in terms of, so this is for the cell throughput, and in terms of mobile throughput, of course, the femtocell users, since they do not really share their access to the others, they've got, let's say, the better throughput, being it on average, or why the other users, even with MIMO stuff, have to share. Okay, maybe I will stop there. Maybe I will stop there. Or I can, okay. I mean, this is a sum up of what we saw on that. This was just some kind of introduction to what system-level simulations can bring to evaluate interference management in such interesting scenario as co-channel deployment. Yeah.
Any further questions from the audience?
You are hungry.
Nah. Well, I'm curious about the still very high outage levels onto the macrocell user. I mean, would they tolerate something like 10%, even 2%?
No.
So, voila. How do we go about it?
Oh, those was just classical solutions. Of course, there is room for improvement. There are other means. I mean, to reduce that a bit further.
Okay, so this is
the co-channel stuff.
Right.
Just do not think about carrier aggregation stuff and so on. But with carrier aggregation, you see
gets
that
better.
you can
play
switch,
around.
play around. But if you just look at the G factor itself, it's a bit difficult. So you have to incorporate in your power control mechanism some kind of networking that we've done in the femto, some kind of more intelligent sensing, not only the macro but the femto as well, and rely maybe on the user feedback as it was proposed, but in a realistic way. Those measurements should come from the femto users because those are the ones connected to the femtocell.
Okay.
Because the trapped macro users won't be able to report anything to anyone.
Okay.
But those kind of things can be aided. So, of course, one of the conclusions is that there is plenty of room to improve that a bit further, and that system level simulation will allow you to
test that. Yes. All right.
On a large scale.
Okay. So if there are no further questions, thank you very much.
Thanks.
And we're ready for lunch. Thank you.
Tu veux PDF ça?